But we have a quiet room here today, so this is my greatest pleasure to introduce you, Dr. Can we quiet?
Not yet.
Yes, Dr. Anthony Chen. Anthony is the fifth-year PhD student from HCI Institute at Carnegie Mellon, and Anthony's work is in novel interaction techniques and fabrication techniques. So his work touched upon a lot of areas in computer science, in the human-computer interaction. So I consider Anthony a star. I consider Anthony a super rock star in the market. In fact, he is in the market. I consider him a rock star, and he published tons of papers that we study a lot in this lab. We study the technique he used in the research. We studied the style he used when he read the paper. So basically, I'm a big fan of his work. So there's a personal connections, right? Anthony did a postdoc with Saul Greenberg from Calgary. And,
Master.
I did a postdoc. I did a postdoc with Saul Greenberg in Calgary, and Anthony was Saul Greenberg's master student. Saul Greenberg basically he's a pioneer in human-computer interaction. Right. So with that, I would give the rest time to Anthony Chen.
Hey, thank you for having me. I'm kind of in the middle of revamping this talk, and it's great we have a small audience. So please jump in if you have any questions. All right. So before I start, this is my laptop. I would like to give credit to all my awesome collaborators. None of the following work would have been possible without these people's great contribution. So I'm trying to think about what I do, and I come up with this term called expressive computing as an umbrella term to encapsulate all my work. Basically, I build interactive systems that enable users to expressively convey intents and ideas in either digital or physical forms. All right, I'm gonna give you some examples. So here are my previous projects. I built such expressive computing systems across a variety of different devices, from styluses to wearable and mobile devices to appliances and to the more recently emergent fabrication machines. So I'm gonna give you a very quick flashback of some of these projects. So I built this stylus that can splatter digital inks on the canvas to support artistic creation, and a very tiny keyboard on your watch to allow you to type for over 32 words per minute. And by looking at...
What if you can't type 32 words per minute even on an ordinary keyboard?
You can learn and achieve that.
Okay.
So you just saw what's a smartwatch that can tell which part of the finger is touching the screen of your phone. Just like correlating the signals between two devices, you can add expressive interaction. And you can also detect which part of the user's body is being tapped by the phone. And by emitting a human inaudible sound, you can detect when the headphones are removed from the ear. So you can pause the music when they're removed and resume it when they're put back. And to use an appliance like a printer, simply take a picture and it's connected to a phone, and the interface provided for the users directly use the appliance from the mobile device. So I hope we've seen a great space for interacting with this device expressively using the systems I built. However, I wasn't quite satisfied with all these previous devices on the left, and became more interested at fabrication machines, primarily because with fabrication machines like 3D printers, the eventual outcome is something physical, tangible, something we can actually have in our real life. So my thesis kind of focuses on this sub-area. So what about fabrication machines? I think the ultimate vision of it is that in the future, hopefully not so far, people will be able to use a suite of computational design tools to fabricate physical objects for diverse purposes. And my research in this sub-area focuses on computational design tools that enable people to do so. So what design tools enable people is allowing them to create objects. And in the sense of computer science, is similar to programming libraries and toolkits that allow people to create and users to create applications. So today I'm going to talk about an approach I developed to build such computational design tools called co-design of form and function. So I'll start by relating back to more computer science perspective, talking about personal computing and going from there to connect to personal fabrication. I want to point out that design tool is the bottleneck, and I'm working towards a co-design of forms and functions, which I'll explain a few slides later, and I'll talk about 4 different projects that instantiate this idea of co-design. So relating back to more CS perspective, how many of you have seen this image before?
The first computer is the
First personal computer, yeah. It's on the 1975 January cover of this Pop Electronics magazine. So it's this device that triggered the era of personal computing, where companies like Apple and Google were born, whose products are still influencing our day-to-day life. So the reason I mention personal computing is that around the year 2005, the notion of personal computing actually triggered some innovation in personal fabrication. So this happened in Cornell University. Basically, a bunch of people from mechanical engineering are thinking, why can't we do the same thing like personal computing, but with manufacturing? So they invented this kit that allowed people to assemble their own fabrication machines, aka a 3D printer that can produce physical objects. So to me, the greatest thing about fabrication is that it bridges virtual and physical world by allowing people to turn their design ideas into physical objects. And the market is seeing a kind of surge in the recent years. It's predicted that by the year 2020, we're going to almost double the market size of 3D printing as of this year. And you can see that it's not just for hobbies doing home projects, it's becoming more and more pervasive. Automotive design, aerospace and defense engineering, tools and components, architecture designs, all these areas are trying to adopt 3D printing as a new way of manufacturing things. So what this tells us that we're looking at a very broad set of audiences, ranging from professionals to casual hobbyist makers. Many of these probably have no or little expertise of using the traditional design tools such as AutoCAD. So what traditional design tools fall short is that they force users to go through a very tedious and complex process of manipulating low-level geometry. Essentially, if I want to make something, I have to start from very low-level primitives, manipulating triangles and faces, shapes, in order to achieve what I eventually want to design. So why is this a problem? Because it means as machines become more and more capable, design tools seem to have become the bottleneck of fabrication. So this is HP's Jet Fusion 3D printers, whose goal is to be able to customize the material property of a 3D object down to the voxel level, which is the 3D version of inkjet or laser printer, which can customize each pixel of a 2D image. So machines have become so capable that they are becoming much better at making things than humans can possibly design them. Which begs the research question: how can we build tools that can better support users' design tasks, going beyond the traditional way of doing design through manipulating low-level geometric forms, but instead supporting users to go higher level up, specifying the functions of their designs. So this research question inevitably touches this notion of form follows functions. I don't know how many of you have heard this before, this term form follows function. It's a term from architecture, which means essentially the generalized notion is that everything's shape has certain functional meaning. If the function of a certain thing doesn't change, the form or the shape shouldn't change it as well. So inspired by this notion, I'm taking a different approach towards making design tools. I take a co-design approach, which means that instead of designing function via geometric forms, I want to go towards a direction where we generate geometric forms, which is driven by functional specification, analysis, and user interaction. And in the following work, I'm going to focus primarily on geometric forms. So we're going to see a series of projects that instantiate this idea of a tool framework for co-designing form and functions. In my projects, I build a series of design tools that go through this high-level tool framework, which I'll explain later in each individual project. So in the first project, Encore, the idea is to extend existing objects' functions with new forms. And the next project, Reprise, is about adapting these objects' functions. And then Facade retrofit existing forms for universally accessible functions. And finally, Forté optimize users' created forms to meet certain function requirements. So let's look at the first project, Encore. So we probably all accept that existing objects have some sort of permanently fixed functions until personal fabrication machines like 3D printers actually allow users to extend these functions. For example, look at this teddy bear. By default, this is probably a bear that you can place on your table, on your bookshelf. But with 3D printing, we can potentially extend this bear by adding, for example, a magnet holder on the bear, so you can actually stick the bear on the, for example, on the fridge. So this somehow changes the functionality of this bear. And with scanning technology, we can easily capture existing objects' shape, which serve as input to process this object, and then to add an extension we want to extend the object's functionality. So this asks two basic questions. First, how to design and fabricate extensions to everyday objects, given the user selected attachment point. And the second question is, if the users don't have a clear notion of where to extend a certain object, such as on the bear, how do we inform the users, given multiple possible attaching points? So let's look at the first question. I'm going to show you a quick demo of how this works in the tool. So the input is the geometry of the teddy bear, and the user, in this case, selects the back of this teddy bear. And then the system computes and analyzes how to add a new component at that point, and generates the support structure as well as connecting structure that can enable a 3D printer to directly add a new piece onto this existing object, extending its functionality.
Is this done manually, or there is any source of intelligence behind that?
Which part?
The stick you printed on the back of the teddy bear.
The only manual part is when the printer automatically pauses, the user will take the bear and then insert it. And then press a button, and then everything will resume.
No, I know, but the notions of creating these sticks, where to put this handle, etc. All of
Where?
that.
Yeah,
the
where?
teddy bear.
Yeah, the user can select where to attach
Okay.
on teddy bear, and everything else can be analyzed
Yeah,
automatically. Okay, so how is this different from conventional 3D printing approach? Conventionally, we assume the object, extension or whatever, is printed on the flat surface. But in our case, this surface could be kind of arbitrary. So the first step in this tool is to generate a connecting structure called connector. So first, we need to analyze the geometry of the attaching area, and then avoid collision, avoid driving the extruder of the printer into the surface by simply raise it above the highest point around the area. And then the next step is to establish the connecting structure by doing what we call bridging. Essentially what it does is it tries to bridge this valley, and as it does bridging at each layer, eventually it can approximate a kind of flat connecting surface we want to establish. And we can compute how many such layers are required by analyzing the attachment area. And one natural question, if you look at this process, well, how well does this really attach compared to the conventional approach? And which I'll get to that in a few slides. But first, we need to address a few edge cases. For example, if the highest point rod area is so much higher than the rest, then which means there is a big drop when the extruder tries to make the connecting structure. So in this case, it exceeds the maximum drop, so the connecting structure is not going to attach well. Another edge case is, well, it's fine, you can raise the extruder, but somewhere above the area there might be some other structure. So we also need to detect that and prevent that from happening. Okay, so given all these analyses and considerations, we can now orient the teddy bear, compute the starting point of the attachment printing, and then also generate a support structure to hold the bear in place. And then the printing process starts. So the first step is to print the support structure. So as they are printed, the user inserts the bear into these structures, which naturally also brings the bear to the point of attachment, which means that without using any computer vision, we can automatically add a new piece of attachment precisely at the user's specified attachment point. So to evaluate how this approach works, I conducted a physical experiment. Basically, I printed some attachments, and then I tried to pull these attachments using the technique by measuring at what's the reading of the scale at the point of fracture. And I compare this technique called print over with existing printing everything in one piece approach by varying the curvature of the surface. So along this direction, the curvature is increasing, and we can see that both techniques suffer from the increase of surface curvature, and in particular, our technique, the print over technique, suffers even more. So this shows the trait of this technique. So to summarize the study, the pro of this technique is there is no need to print object and attachment as a whole. Instead, we save time and material. But the con is it's not as strong as shown in the experiment as we're printing everything. Another limit is about material. So we assume that they have similar thermodynamic material between the objects and the attachments. If in cases like you want to attach something plastic to a piece of metallic object, then a simple approach to work around that is to add a thin layer of glue, which adds a universal medium to kind of pull two different objects together. So to answer the first question, how to design and fabricate extensions or attachments to objects. Then the second question is, how do we know where to attach if the user doesn't show a preference? So this is done by performing some analysis of the objects we call attachability. And we want to visualize this information to the users to inform their choice of attachment area. So the first metric is flatness. So if the object surface is flat, then it's perfect. If it's not, we compute the average distance from the user selected area to the connecting structure, the connector. Another metric is moment. So this needs to be considered if there is a load at attachment point. So in the case of teddy bear, assuming it's going to be stick to the fridge, then the weight of the teddy bear will give the moment at the user selected attachment point. And we can compute that moment, and we can visualize all this information on the surface of the teddy bear to inform the goodness of attachment. We can also keep adding this kind of metrics, and the user can explore these design options by giving them different weights. So a very useful example is if a user gives more weight a moment, then the good area will concentrate towards the center of mass. And if the user gives more weight on flatness, then you can see the green or good area will concentrate on the flat lateral area of this range. So that's the print over technique, printing new parts directly onto existing objects. So returning to the framework I mentioned earlier, it starts with the user interactively specifying functional specification, in which case the functional requirement is to be able to attach something to something else. And then it goes through analyzing the attachability of the object, allowing users to explore different attachment points, and also generating the support structure, the connector, and to finally generating the printing and processing instructions, automatically pausing the printer, in allowing people to insert the teddy bear and then resume it. So under this tool, we can also explore the different techniques such as printing through existing objects. So how does that work? Imagine you're printing a label for this pair of scissors. You can actually pause the print and in the middle insert the scissors. So you can print this label through the handle of the scissors. And when it's done, it's naturally interlocked with the object without using any adhesives or fasteners. So here I want to kind of emphasize on the importance of providing analysis and interactively with user editing exploration. So the basic approach of this idea is we want to print something through something else, such as the printing this square while being able to let it go through the ring. So the user would start by interactively positioning these two objects together, so that's the functional specification. But in some cases, it's not obvious whether a given configuration would actually work. So here's a quiz. Given this configuration, and we're printing this larger structure this way, at which point do you think I should pause in order to put the ring through the partially printed structure? Do you even think that's possible?
Can you rotate it?
Right, you need to rotate it. But at the first sight, it's probably not so obvious. So as an end user, you probably don't really get that instantly. So that's why we need certain analysis, simulation to inform the user whether a certain configuration is actually feasible. So first, the tool turns on the physics engine, and the ring would drop under gravity. So this simulates the final position of the ring should it be able to be inserted. And then as the square is partially printed, this is what it looks like. Then the question is this actually feasible? Well, in order to know that, we simply reverse the gravity. So this is similar to taking the two objects and then rotate them. And if the ring falls, which means there exists a path for the ring to be inserted back into the partial structure. So if you see something like this charm is escaping the partially printed bracelet, it means that there is a way to insert it back in at the middle of the print. So this is Project Encore. It extends existing objects' functions with added new forms. The next project, Reprise, kind of explores the design of such extensions or attachments. In particular, the goal is to adapt existing objects' functions with these new forms. So we have very specific design goal of adaptation, which means that we want to add components that can mechanically modify or enhance certain function of objects, such as this green structure that can help you fasten or stabilize the drill bit as you try to sharpen it. And the more generalized reason of needing adaptation is that most common objects sometimes might not work for certain uses or use cases, such as young kids might not be able to reach the faucet. So it's important to add this faucet extension in order for them to use them. So these are kind of great such adaptation designs, but it's not clear how an end user can actually go about designing them. So in order to understand the design space, I surveyed over 3,000 examples through books and online communities. And the goal is to to understand the main strategies of designing these adaptations. So I summarized the 5 major strategies. So first one is wrapper extensions, such as the wrapper around the handle of bucket, or extending the ones that extend the zipper pull on your backpack. The second class is handle, such as the one that help you hold a knife. The third class is lever, such as this one that help you turn the knob. The fourth class is anchor and stand, such as the one that fixes these nail cutter on the table. And finally, we have guide. So this kind of interesting discovery. Some people actually cut out this cardboard to make it easier to locate and press these buttons. So with these strategies, as well as the type of action they support, I construct these kind of design space in this table, which is actually a lookup table. It's nice because you can actually, as an end user, if you want to design for a certain object, you simply look at what type of action you're doing with these objects. Is it static, like holding? Or is it linear, like pushing, pulling? Or is it rotation, such as clutching or turning? And then you can look up this table and see what strategy is applicable. So with this kind of design space as the foundation, I developed this tool called Reprise. It manifests the knowledge of adaptation into a simple and executable workflow. So I'm going to show you a demo demonstrating how this tool works. So imagine Larry, an occupational therapist, helping a patient adapting a pair of wire cutter, as the patient recently suffers from hand injury. So Larry goes to Reprise. The first step is to interactively specify the action of this object, this wire cutter. And the virtual hand will help Larry specify the orientation of grasping one of these handles. And then Larry selects the type of action. So in this case, or selects the type of strategy. In this case, the wrapper that can help user grasp the handle. He can also adjust the design parameters, making the wrapper longer or making the wrapper thicker in other cases, or adding small bumps on the surface to tighten the grip. And then exports everything into a 3D model and then prints the wrappers using soft material. So this eases the user's grip on the handle, but it doesn't solve the problem of clutching them. So Larry goes back to the tool and selects a different type of action, clutching. And by simply clicking on the 2 handles and then at the pivot, he specifies the 2 clutching arms. Then he generates this lever structure that can decrease the force required for clutching the cutter. So it reduces the force, but it makes the cutter overall too large. So Larry has to go back to the tool again and iterate on the design. So he removes one of these levers, and instead he tries to add a structure that can anchor the whole thing on the physical surface. He also adds some anchoring or attachment structure to help attaching this anchoring structure on the handle. So it turns out this is the best design the user likes, which enables him to use the cutter using just one hand. So this demo kind of illustrates how Reprise's workflow enable people to design adaptations. And again, you follow this framework, starting with specifying the type of action the user is dealing with, analyzing the geometry of the object, and providing adaptation strategies, generating accordingly the geometry of adaptations, where the user can then edit and explore different design parameters, and finally adding the attaching connecting structures and printing and processing to finally produce the adaptations. So to validate this tool, I replicated all these 15 of the previously found examples, each of which representing a dot in the lookup table. So you can see how you can design these levers to help squeezing a spray bottle, something to help you open the closet door, or opening this jar, or handle to secure the grip of the Sharpie. Or this guy that makes it easier to put the Sharpie back to the cap. And you can actually kind of combine different adaptation strategies together. So this entire thing has a guide, a handle, and an anchor. In some cases, you can adapt certain things differently. So this ring helps you turn the key, and this guiding structure helps the user put the key back into the lock. So that's Reprise. It adapts existing objects' functions with new forms. So from this project, we also learned that even the most common everyday objects sometimes might not be physically accessible to certain people. And if we keep looking, we can find probably more such accessibility problems. So what do you think are the problems with these microwave oven buttons? Do you see any problems? Any reason why certain people cannot use these buttons?
Complicated.
No.
Yeah, there's one issue. Yeah. Besides that, something that's more fundamental.
No haptic.
Yeah, precisely. They are flat, providing no tactile or haptic feedback for visually impaired people. So we kind of look at how 3D printing or fabrication can help solve this problem. So looking into a different project that retrofits existing forms such as flat buttons for universally accessible functions, such as pressing them or knowing what these buttons actually are. So this video shows the entire process of making these buttons usable or accessible. User starts with taking a picture. So this is blind user by the way. There's an audio guidance from the phone to help a user take a picture. And the dollar bill serves as a spatial or measuring reference. So once a picture is taken, we go through some computer vision analysis to identify the area of interest and provide an image to the crowd using mechanical Turks to label the spatial and textual information of each button, and then send the information back to the user, which now the microwave oven becomes kind of a graphical user interface. User can actually explore and can then customize how I want to add tactile feedback, add braille or other legends, or simply add some acronym letters. So
Can I ask a question?
yes.
So who actually put that dollar bill on the microwave?
In our experiment, we put the dollar bill, but in reality, the user can also put the dollar bill on the surface of the appliance, close enough to the control panel.
Right, but the user is visually impaired.
Yes.
How actually a visually impaired can precisely put that dollar bill into the right position?
I don't think it requires the precise position.
Oh, okay.
As long as it's present in the image, we can run analysis. We can obtain the dimension of dollar bill and compare it to the buttons.
I see.
So it doesn't have to be at a precise position orientation.
Okay.
So in this process, the user starts by taking a picture of the microwave oven, telling the system that I want these buttons to be useful. And then we use computer vision techniques to match the dimension from dollar bill and identify the area of interest. Basically, it crops the control panel and then send it to the crowd using crowdsourcing to label the positions and text on these buttons, which then allows the user to explore the information on the phone interactively and identify what they want to add as tactile feedback. And finally, generate 3D model and bring the tactile layers to be added to the appliance. So in our study, 11 blind participants were able to independently create, affix, and use tactile overlays onto appliance interfaces. So that's Project Facade. We retrofit existing forms for universally accessible functions. So So looking at the previous 3 projects, something that they have in common is they are all incremental extensions added to existing things to augment functionality. However, there is a larger set of objects such as furniture, which is standalone and nonetheless able to support and interact with other objects in the world. And more importantly, users might find it difficult to design such objects because some functional requirements are more expertise required. On the other hand, engineering methods can verify whether a certain piece of design actually works, but they do not naturally support users' creative process. So I then look into this problem of kind of combining the user's creative forms to meet functional requirements that are usually achieved by running some engineering methods such as optimization and simulation. So this is an earlier prototype of this ongoing work. It shows that user is drawing a skeleton of a chair, and then the user also annotates this functional requirements, saying there's just force on the back of the chair, and I want this empty space for a person to lean on it, and as well as force on the bottom of the chair and some empty space for someone to sit on it. And finally, this chair is positioned on the ground. So with this information, after the user draws the design and annotates the functional requirements, we can then run a finite element analysis, which potentially analyzes how this design, this basic material will deform under the load specified by the users. And then we can use optimization process to generate a structure, some sort of structure whose high-level goal is to resemble the user's original design, but with built-in structure that also satisfies the functional requirements. And the users can go back and then maybe change their sketch or adding new features or removing some suggested structures. And through this process, eventually you want to be able to combine users' specified or designed form as well as the functional requirements that need to be met for this particular object, a chair. And finally, the end goal is to be able to create such objects such as furniture. So I want to talk a little bit more about optimizing form and function together. So the original method is from a paper around 1999 using a compliance minimization approach. The basic idea is starting with a block of material. I want to selectively and a bunch of other these parameters such as the amount of material on the use, the properties of material, the loading forces, the boundary condition. I want to selectively look at these pixels, adding or subtracting weights. So eventually you can imagine carving this material and then what is left is a structure that meets all these requirements. So we can look at the detail of this approach, which basically at each pixel or each element, what it's trying to do is it tries to minimize the compliance or deformation of each single element by changing the weight. So conceptually, we can add to this optimization term by adding to the compliance with something different, something that represents how far away a certain structure is deviating from the user's original design. So basically, we're adding a distance field. So for each element, we know whether this element is on the user's design or it's very far away from it. Another way to look at this is we can consider compliance or deformation as function, which is what we want to achieve or satisfy, given the load on the chair. And we want to add a term describing the form, which means that we also want to keep the user's original design. So by adding these two together, the eventual goal is to create objects co-designed with the user's provided forms and functional requirements. So in doing fabrication research, I believe this notion of deploy or destroy. So I'm actually using these two brackets. So in my previous talk, I said no accident so far, but unfortunately, a few days ago, they broke. And this is not naturally, I was trying to remove the monitor and I broke them. So, but it's nice to see how the things you design or designed by your research actually work in reality. So I've told you about 4 different projects. So you can see each of them have something related to forms and functions. And to recap, we are looking back again at this framework. I figured that with all these tools, we can always start with users' interactive specification of functions, going through some sort of analysis iteratively between analysis and users' editing exploration, and the generation of geometry. And through this process, can eventually produce printing and processing instructions. And this is what I imagine as a high-level and generalizable framework through which you can achieve co-design of form and function in computational design tools. And some unanswered questions so far for future. So I want to consider more interaction methods or techniques in this framework. So at present, we can understand people are looking at a flat screen and then everything is projected from 3D to 2D, which is very unintuitive and difficult to grasp in direct manipulation method. So in the future, I imagine that we'll have effectively more emerging or immersive environment that can merge design and fabrication together as an integrated space, such as using augmented reality devices such as the Microsoft HoloLens. So imagine that in the future, users put on the AR device and they can look at a chair, say, I really like the shape of this chair, and I can just obtain the geometry, taking it as my starting point. I want to work on this geometry inspired by existing objects. And as I work on my design, I want to put it back into the physical environment to see if the chair I design actually fits with other furniture in my living room. And as I finally am done with this design, I want to actually manufacture it. So by projecting this virtual information into the physical space, I can experiment with different material and assemble them together to actually make the physical design. So besides interaction, I also want to look into more domain knowledge, which means that instead of a general design tool, I want to be able to consider domain knowledge for people from other disciplines. So imagine a teacher or educator trying to design and fabricate a kit allowing students to learn physics, such as how this catapult works. So how can we provide a design tool for a teacher that incorporate the knowledge of physics as well as learning science and other domain knowledge? So one potential output of this tool would be this kind of kit that allows students to actually make a catapult and see how different design parameters can affect how it works. Another scenario is relating to developing countries and disaster relief. So 3D printing can be potentially very useful in this scenario because of the limited resources and the emergency of using life essential things. And one very interesting research question is how do we actually reinforce and fix these everyday things so they can stand strong in the face of disasters. And this requires much more domain knowledge than mechanical engineering. There are also other economical or environmental considerations that need to be considered. Also, as I showed earlier, in the future, 3D printers will be able to design and fabricate material at the resolution of each voxel. So how do we provide design tools that consider the material science perspectives, educating users what material to use and how to use such material at the right place of the design. So I think all these domain knowledge is very important to be incorporated into future design tools. So to summarize, we started all the way back from 1975 looking at this very first personal computer. And Intel tells us that in just 4 decades or so, we've already achieved over, I believe at this point, way over 1 billion personal computers. Which really begs the question, what if personal fabrication machines can undergo the same kind of growth pattern? So what would happen in the future? Or more importantly, where are we right now? Which means starting from the very first fabrication kit from Cornell, we can kind of estimate our current position on this curve, which really tells us that in the future there's so much to do. And personally, that's why I'm really excited about this space. There are a lot of unsolved questions, and it's really interesting to look at the challenges from the perspective of human-computer interaction. So with that, I want to conclude my talk, and I'm happy to answer any questions. Questions, folks?
The bottom picture, you know it's a bracket on the left, it looks like a slingshot on the right, but what about the other two guys?
Yeah, this is a mustache shopping bag handle I designed.
Okay, all
So
right,
you can throw
cool.
a shopping bag, so you can carry two. And this is a hook.
Okay, just to hang a coat or something.
I don't know if like a user would have access to both of the tools, but how would a user know if they wanted to use like Encore versus Reprise? Because it seems like they're somewhat similar, but like have
Yeah.
very different results.
Yeah, Encore focuses on just attaching A to B.
Okay.
And Reprise is more specific, focusing on adapting the everyday object. So you want to make certain action with an object easier, or make it more effortless. You can use Reprise. So Encore, in some way, is more general.
Okay.
So what do you think about future of personal computing? Are we going to stick with 3D printers, or do you expect new technology is going to come to help us to fabricate?
Yeah, I think, I believe personal computing is becoming more and more physical. And fabrication is just one instance of becoming more physical. Another instance or example is Uber. So Uber, the outcome of Uber is not an algorithm or some results from some data science or machine learning. The outcome of Uber is a car driving itself. So it's very physical. There's a lot to consider than just pure artificial intelligence or algorithms. Questions, folks?
Do you have any idea on the shape-changing devices? Because I think I saw one of very interesting books from XD designing something around the smartwatch shape-changing. Do you have any notions on this, or do you have any work on it?
Yeah, I have been thinking about one interesting way to combine this work with that would be to allowing users to fabricate ways to do shape changing with everyday objects. So the larger goal of this would be trying to bring robotics to everyday objects. And this really needs fabrication because everyday objects are so vastly different. You can have a one-size-fits-all way to do that. For example, if you want to help a person automatically open a door, or pulling out a drawer, or doing some heavy lifting task, they really need to analyze that particular scenario and have customized structure to do that. So in some way, I think this related to shape changing because they are kind of actuating everyday objects, but also related to fabrication.
There's a pretty interesting list of projects that you zipped through before you began for 3D
Yeah.
printers. Which of those has been the most successful?
How do you measure success? I have some my personal favorites.
Actually, your personal favorite would be the best answer.
Yeah, my personal favorite is the project where I combine the phone and the watch together, correlating the signals between two devices. And this, back then, really opened up a very large space of developing new ways of interacting with devices. So I showed example of looking at a watch orientation, which can tell which part of the finger is touching the phone screen.
Right, yeah, that's pretty neat.
Yes.
So I'm quite interested in the furniture design project issue. So Google has a product like you can draw a sketch and you will create like a sleek icon or something. Do you think it's a good way to integrate your design techniques and their product to make the user interface more easy to?
Yeah, I think it's possible. Although I'm not very familiar with Google's project.
It's just you can draw a rough shape of a chair. You
I
will
see.
generate like a
An
perfect
icon.
shape of a chair.
I see. I think there's some sort of intelligence or data-driven approach in that it kind of take the user's input as query and then maybe retrieve some templates and then kind of fit the two together, which in essence is similar to Forté that also transform users' input into some design that in some ways better. For example, structurally strong.
So I have this question. So we talk about cross-sourcing. We talk about personal fabrication. So which way is the future?
Cross-sourcing.
So
Right,
I'm thinking I don't need to fabricate myself, right? I just ask people to do it for me. Probably can send it over to me. Like, if it's really crowdsourcing, I can imagine that somebody in the Hanover area and they work together to work on a project and get delivered to me pretty quickly. Versus I do have to fabricate by myself. Which is going to be the future?
I think maybe the combination of the two. You can't really get the crowd or any other methods to replace your ideation process. You still want to have the originality of your ideas and express it in some ways. And then maybe the ways to actually realize your ideas can be either crowdsourced or more traditionally manufactured or using 3D printers.
So why do computer scientists care? How we as a computer scientist can actually help to
Yeah.
sort of.
That's a good question. I think relating to one of the earlier slides, similar to how we've been developing toolkits and libraries that enable people to write applications, we're doing something very similar. We are providing design tools that can enable people to realize their physical ideas. So there's a lot to be learned from the CS approach of working on toolkits and libraries and how that can be applied to design tools.
All right, let's thank Anthony again, please. All right, cool. It's a very inspiring talk.
Thanks.
All right, thanks everyone for coming.